Hello, my name is Samy Bengio, and I'm a research scientist at Google, where I lead a team, the Google Brain team, who's interested in trying to better understand machine learning in general and deep learning in particular. Today, I'm going to talk about one particular topic that is dear to my heart, trying to better understand why deep learning works. Um, I'm sure you've all heard in the past few years about deep learning and how it has actually caused quite a revolution in the machine learning field. You can see here, for instance, the number of times that people have been searching deep learning on search engines. And it's been growing exponentially fast since the last 7, 8 years. Uh, Another way to see it is the production of research that is happening in the past few years. So most machine learning researchers now post their papers, their articles online on the archive. And we can see the number of papers about machine learning has also increased exponentially in the past few years, actually faster than what Moore's law say about the increase of compute power. So that's also interesting. Yet another way to see it is the number of people who yearly attends the biggest machine learning conference we have, which was called NIPS and now called NeurIPS. So you have here the registration numbers, and you can see that they're also growing exponentially. And I can tell you, because I was a program chair for NeurIPS a couple of years ago, that the main thing nowadays that stops that curve to go even faster is our inability to predict how big we need to uh, select the venues a few years ahead. And so the size is actually capped by the venues that we can find. We've actually computed with my co-program chairs a few years ago when the total population of the world would actually attend NeurIPS, and we've estimated that this would happen in 2048. So get ready, it's coming for all of you. Now, what's going on exactly? What's special about deep learning, and how is it different from what we've all used to be calling artificial neural networks, which were there for decades? Uh, well, there's a couple of things. First, we have a much bigger compute power, and this is paired with the fact that we have much bigger um, data sets. So data sets now are in the hundreds of millions sometimes, where they were more in the hundreds back then. Compute power, so computers have become much faster and bigger, but we also have specialized hardware like GPUs and now TPUs. Um, on top of that, researchers have developed multiple new techniques, both for training faster, but also for training better. And that also helped. All of these compound uh, together actually make the big difference. And that's why now it's working much better, significantly much better. So we already know that there's multiple things that we could do with neural nets. You've heard, for instance, about image classification, where you go from pixels to a class. This is an image of a lion, for instance. Or speech recognition, when you go from the audio to a sentence. So here we decode how cold is it outside. Machine translation, where you go from a sentence in a language to the translation in another language, from hello, how are you, to bonjour, comment allez-vous. And finally, image captioning in the past few years, where you again go from pixels of an image to a long sentence describing the image, like here, a blue and yellow train traveling down the track. So is this real, or is it just hype? There's a lot of hype for sure in the media, at least, but we think that this time it's actually real. If you take a company like Google, tons of their products today are using machine learning and AI. I'll give you here just a small list, but these are applications that you use every day, likely, like the Assistant, Cloud, Android, Google Maps, Google Search, of course, Gmail, Google Ads, YouTube, Translate, Photo, Drive, Apps, and many more. So I can safely say that today, machine learning is not just hype, it's actually used in many places, and it actually helps improve all of these applications. So the only concern that I see today is that we don't always understand why it works. And that's concerning because we also need to be able to know when it's not going to work. So today I want to present a few small vignettes of some of the work we've been doing in our team. And the first one, understanding deep learning requires rethinking generalization, is actually like the starting point of a big body of work that has been trying to understand what's going on in terms of generalization in deep learning. So this work has been started by Qinyuan Zhang, who was an intern back then, but now he's a fully research scientist in our team, and together with other people in our team, it was presented almost 3 years ago at ICLR, one of the big deep learning conferences. So we know from the theory that we have good reasons to think how models and why models are actually working well on new data. So the blue curve on this graph shows how the training error, so the error that we get on examples that are in the training set and that are used to train the model, is going to go down as we increase the size of the model. So if we have bigger models, we should be able to train better. We know that. We also know, and that's the red curve, that for new images, for new examples that have not been seen by the model, the curve will also go down, but until some point where it will start going up. At this point, we say that the model is overfitting. So it's going to kind of learning by heart the training examples, but not understanding how to generalize to new examples. And that's where you usually want to stop. So this theory has been known for decades. The problem now is that today in the deep learning era, we have very big data set, but even bigger models. So here are two examples of data sets, CIFAR10 and ImageNet, that are used in image recognition nowadays. Uh, CIFAR10 has 50,000 examples and ImageNet has 1.2 million training examples. And you see examples of models that are known in the literature and how big their models are in terms of just raw number of parameters. So you see for CIFAR that you have models that are in the millions, and for ImageNet in the hundreds of millions. So these models are orders of magnitude bigger than the number of training examples. And this is surprising. So there's a natural question that everybody has been asking is deep learning just a giant memory because we have so much memory in this model that we could just learn by heart, or is it actually generalizing? Well, here's the experiment that Shinran conducted. He said, let's try to learn our training set, but force it to learn by heart. So we're going to actually randomize the labels of each of the training images. So for instance, this image on the top here of a dog, a husky, instead of saying it's a husky, we're going to tell our model that it's a whitebait, like a random other label that has no relation with the husky. And we're going to do that for all training examples. What's going to happen is, of course, we are not going to be able to generalize. It's impossible when you say to the model that this husky is a whitebait for this image of a husky, and then for another image of a husky that you say it's a carnivore, that it can actually learn anything useful. So what happened when we did this experiment? For each of the model, like Inception, AlexNet, MLP, and AlexNet again, we train once with the real true label and once with a random label. What we observed is in both cases, the model was able to learn by heart all the training examples. So the train accuracy was 100%, or the train error, if you want, was 0%. Of course, the test error is a different story because it's impossible when the labels are random to be able to answer correctly on a new image because there was no information in the train set. So the test accuracy is very low when it was random, but the surprising fact is that the test accuracy was still very high on the test set for when labels are okay. So the same model with the same process, with the same size, is both able to learn by heart and generalize. And this was very surprising. We actually conducted several more experiments while instead of changing the label and randomized it, we randomized the pixels, we changed the order of the pixels, we added Gaussian noise, we tried multiple things, and in all cases, we were able to learn by heart all the images, no matter how we would perturbate the training examples. So these deep nets are really high capacity. Now, what's surprising, of course, is that the theory says that when we get to zero training error or close to that, that's the blue curve, we should be in a regime that is called over-parameterization, over-training, overfitting. And so the red curve should be very high in the sky, which means if we are able to train by heart, we should not be able to generalize. It's at one or the other. But of course, that's not what we observe. So this actually sparked a lot of questions in the literature. Many thousands of papers were written about it, actually. And interestingly, about a year ago, new theories started to appear, and we discovered new things by just people looking more. So for instance, in this paper from the end of 2018, they reproduced the same curves I showed you, but they kept going by training the model further and further along the deep learning regime. And at this point, they discovered what they call the double descent generalization curve. So the test error goes up as expected until training error goes to zero. At this point, which they call interpolation threshold, the test error starts going down if you apply the right regularization techniques that we have all learned to use in the deep learning era. And many other people have observed the same thing since then. And this might explain why, despite the size of our big neural nets, now we can still get training error zero and good test error, and hence good generalization capacity. So this is great news, of course. Um, so let me go on with a second project, which we call Are All Layers Created Equal? This is again a project led by Qingyuan with colleagues from the Brain team from last year. And in this project, we want to understand when we have a deep architecture, a deep network, if all the layers of the deep architecture are as important as the others, or is there specific layers that are more important than others? So the overall questions that we're asking is basically in the same line as other theoretical understanding of deep learning. First, we know that these models are universal approximators. We also know that depth is important. The deeper, the better you can represent compositional functions. And we also know now with the work from Qingyuan from 2 years ago that there's a trade-off between interpolating and memorizing, and deep nets are very good at that trade-off. In this work, we are trying to just understand how, when we train models, usually with stochastic gradient descent, how are the parameters used effectively to actually learn these functions. So here is the setting that we devised. We're going to train the same model, and we're going to look at multiple training epoch. An epoch is when we've seen all the training example once. So you have epoch 0, 1, 2, up to t. That's what's shown in the graph here. And we're going to just remember all the parameters at each epoch. And we're going to do some tricks. So at the end of training, we are doing what we call a whole layer reversioning. So we take one layer, in this case layer 3, and we, after training, we replace the parameters of that layer with the initial random parameters, the parameters that were at epoch 0, that is the random values they had before we start training. So we just change one layer, and we don't retrain, we don't do any fine tuning or anything. We just try them all and see how it goes. We can do that for any layer. Another thing that we can do instead of starting a layer from the initial value is to just instead replace the parameters by a fresh sample of random values. So that's very different from the values that we had at the beginning. So what happens? Here is a graph of an example of graph of what happens. Each column here is one epoch of training. So, and each row is a layer. The color shows the test error after we've applied something. So for instance, in the graph here, we've taken layer 3, and we've replaced the value of the parameters with those of the first of the epoch 0, the initial value, and we've just tested it. And what we see, the color shows that it doesn't change anything. The model is still good. So this graph says that if we change layer 3's parameters at the end of training by their initial random value, it doesn't change anything. On the other hand, if you replace it by fresh random values, that's column 1, then it breaks completely. And it also shows that if you change the models of layer 1, then the problem happens also. So there are a few layers that are critical and other layers are not. You can just replace by their initial value and nothing happens. So this is surprising to us, and we're trying to understand what's going on, why some layers are critical and some are robust. We've tried multiple experiments. For instance, here we tried multiple size of models. So we have, for instance, a 3-layer model and a 5-layer model. And we've also changed the size of each of the layers from 16 to 512. And what we show on the graph is the test error after we do this reversioning trick. So when the model is small, for instance, with a small number of hidden units, the test error will go very high. So reversioning has a drastic impact. It's not good. The model suddenly doesn't work well. But as you increase the size of the model to 32, 64, up until 512, you see the curve going very low. And now the test error for either a 3-layer or a 5-layer network goes down to almost 0. So meaning that changing one layer has no impact on the error when the model is big enough, which corresponds to the current deep learning setting where models are big in many ways. So that's great. In some sense, overparameterized deep nets trained with stochastic gradient descent find ways to tune the layer robustness based on the model capacity. So it's only going to use what it needs, and the rest will just be robust, and you can change them to the initial values. It's going to work. We tried that for multiple other type of model. So this is a VGG, and again, you see some of the layers are important, others are not. These are other VGGs, same observation. This is a ResNet, another type of very popular networks. Again, you have layers that are always important and others that are much less important. Multiple types of ResNet. And in general, what we think is that there's a relation between this notion of robustness and generalization. In fact, it could explain some of the reasons why big network still works, because if you think of it, it means that most of the parameters of a big net are actually not important. If you change them back to a random value, the initial random values, they still work. So they are not crucial for generalization. So only probably a much smaller set of parameters are used for generalization. So that's actually an important thing to note. More recently, someone else in our team, Hani Selki, with her intern, found ways to link these the criticality, how critical a layer is, with the generalization capacity of a model. In fact, they found like a metric, a measure that helps them rank models, and the ranking that they obtain will be similar to their generalization performance. So they discovered a new method to actually order models according to their generalization performance based only on this criticality metric. So that's great, because now we may not need always a test set. We can do it just with the training error, and we are going to have a good understanding of whether a model will work or not. So with that, I'm going to conclude. My goal today was to show that deep nets are great, but there's a lot of things we don't understand about them. For instance, not all parameters or layers are important, and they are not all used the same way for models to work well. It's interesting to explore extreme settings to better understand how it works. I'm also very excited to see that there are new theories of generalization that are still discovered now. And I think we'll have many more years of understanding of deep learning. Thanks, all of you.